Peter Goddard, Director of the Institute for Advanced Study, and it's my pleasure to welcome you here this afternoon for this Institute lecture. After the lecture, there's a reception in Ford Hall to which you're all invited. Today our speaker is Vladimir Vodvodsky. Vladimir has been a professor in the School of Mathematics here at the Institute since January 2002. He obtained his bachelor's degree from Moscow University in 1989 and his PhD 3 years later from Harvard. He was a member at the Institute from 1992 to 1993 and again from 1998 until he joined the faculty in January 2002. In between, he held positions at Harvard, at the Max Planck Institute in Bonn, and Northwestern University. Vladimir's work is concerned with interrelations between algebraic geometry and algebraic topology, particularly the synthesis of two major branches of modern mathematics, algebraic geometry and homotopy theory. His research has influenced the development of both algebraic geometry and topology and led to the solution of a number of outstanding problems, including the Milnor conjecture. His work is characterized by the way it handles highly abstract ideas flexibly so that they can be deployed to solve concrete mathematical problems. He was awarded the Fields Medal in 2002. Today, his subject is Foundations of Mathematics and Homotopy Theory.
Thank you very much. So the kind of work which Peter spoke about was then, and this is now. So that's kind of a new work. And also I want to say in advance that the talk was prepared mostly for non-mathematical audience. So don't expect many detailed formulas and stuff like that. Oop. I'm sorry, can we break for a second? Who is doing the projector? I'm sorry, we've arranged everything, but now it's broken again.
I think we can do it.
No, wait, I'll do it. Well, at least I know what has to be done. Okay. Nobody else does. Sorry, it was done, but now it's not working again. So let's get back to this adjustment.
Oh, okay.
I don't know why it's again all cut off. Should say PC adjustment. Here. Further down. Here. No. It should be 264.
Is that 263?
263, 264 doesn't matter. Yep, let me. More, let's say 265. More. No, other way around. More, other way around. Let's do 63. Yeah. 62. 61. Let me see what's happened. No, 66. 66. Look, now it's 60. Now it's 66. Okay, one more up. Further up. Further down, sorry. Down, more. sound more. Okay, that's fine. I apologize. This thing had gotten life of its own because we've set up all the numbers correctly in the morning, but suddenly it's all wrong again. Anyway, so right. So the goal of the talk, I want to explain some of the work which I have been doing recently in very broad terms. It's related to the foundations of mathematics, and the first thing which I want to say a few words about is why do we again have to look at the foundations? So people have been interested in foundations of mathematics on and off for centuries, I guess now. And my feeling is that it might be time again to go into the on phase. So the reason I believe we need to look at the foundations is what is called here proof correctness problem. And I think you all had plenty of time to read it. The thing is that as mathematics gets more and more complex, there is an accumulation of results whose correctness becomes more and more uncertain. So we don't know about certain things, whether they have been proved or not. On a smaller scale, kind of everyday scale, every mathematician has experience on both sides of how terrible it is nowadays to be a referee. So I have a paper which is about 10 pages long, and it has been lying in a journal for about 4 years now, because a referee can get through. I have been not much better myself as a referee. So the problem is the mathematics is very complex, and if one wants to be responsible for a paper he referees, it takes an enormous amount of effort. So it really slows things down. We do have to do something about it. Now, from my point of view, there is only one solution, except of just going over everything 10,000 times, and this solution is to start thinking seriously about automated proof verification techniques. And many different things today seem to be coming together to make it a reality. So here is a long paragraph which describes my sort of vision of some ideal world situation, how it should look like in 50 years' time. That when I submit a paper to a journal, I submit a text written for people together with references to the formalized proofs of all the results. Now, these formalized proofs are checked mechanically by a computer before the publisher sends a paper to a referee. So when it gets to the referee, a referee knows that everything written there is proved correctly. He has to check whether or not, first of all, the whole thing is interesting, and second of all, whether or not the statements of the theorems, as opposed to the proofs, have been correctly formalized, so that what has been proved is indeed what has been claimed. So that's some kind of a dream world. So why aren't we there yet? The idea of automated proof verification is a very old one. People started to work on this issue as soon as basically computers became common. And there are two canonical first systems which were developed one, I think, somewhere in Netherlands, and another one in Poland. One was called Automath, another Mizar. So as you can see, it was about 30, 40 years ago. The systems are still alive, especially Mizar. There is still a group who works with it. There are like hundreds, maybe thousands of pages of mathematics which has been formalized and checked with this proof checker. But for some reason, no one knows about it. One of the things I'll try to explain is why no one knows it and why it's actually not usable. I mean, yes, there is a lot of mathematics formalized in these systems, but in practice, they're not usable. So two main lessons which can be learned by looking at this Mizar and Automath and all their descendants, especially Automath has multitude of descendants. So the lessons are the following, that first of all, if one tells to a computer scientist, if one gives him or them a formal, concrete description of a formal system, then it's not difficult to create some kind of proof editing or proof checking software based on this formal system. They're extremely good with it and getting better and better every day. So the real thing which stops the show is not in the computer science, it's in mathematics. So I claim that we don't have good approach to formalizing mathematics. So let me try to explain what I mean by that. And so there is this general picture of what a formalization of mathematics is or should be. So basically, one should say that this side is formal, syntactic, and this side is completely informal, intuitive, Platonic, whatever. They meet somewhere in the middle. So this is some formal language which can be programmed and whatnot. For instance, Zermelo-Fraenkel theory, first order logic. Now, never a concrete formal system describes all kinds of mathematical objects. That never happens. It can always directly describe only objects of extremely special kind. Like the Zermelo-Fraenkel theory describes something they like to call sets. I would not call these things sets. They're actually some trees with no symmetries. So one can only speak in a formal system about objects of this type. And then there is an additional arrow, which is usually sort of glossed over, which I call encoding. Doesn't have a standard name as far as I know. And this is how to translate a statement about general mathematical objects, general mathematical statement, into a statement about the kind of objects which can be directly described formally. So here is an example of, this is the most, this is the canonical formalization, approach to formalization of mathematics. If you say to someone that mathematics has no foundations, then they immediately reply, how so? There is Zermelo-Fraenkel theory. So it's kind of cool on this side. Its major problem is that this meeting point here is extraordinarily narrow. So it's extremely specialized theory which describes extremely specialized objects. It's plausible that all the mathematics, every mathematical statement can be somehow encoded as a statement about objects of this form. But it's by no means a natural process. This is actually where all the current approaches to formalization fail. It's in this arrow, in the encoding arrow. So this is something computer scientists are good at implementing. But the practical translation into this special kind of terms is usually very difficult. Now here is, from my point of view, what is the key difficulty, sort of the real most serious problem with all the existing formalizations. And that's what I'm going to concentrate on, and that's what will later get related to the homotopy theory as promised. So there is this equality problem. So when mathematics is done, well, there will be, let's go further. I'll give concrete examples. We'll see what I mean by that. So here is one example. That's the most complicated formula in the talk. So let's see what's written here. This says that the sum of natural numbers I from 1 to n is given by this formula, n times n plus 1 over 2. So that's a very simple formula, easy to prove. So for example, it says that like the sum of first 10 natural numbers will be 55 if I didn't make an arithmetic mistake. Now here is exactly the same formula, except now we say that it's a sum of integers, also from 1 to n. So for a mathematician, these two statements are obviously equivalent. No one will even think about proving that they're equivalent. As soon as one tries to explain this stuff to a computer, to formalize it, in all the standard approaches, this equivalence disappears. It especially disappears in the Zermelo-Fraenkel approach, where from the Zermelo-Fraenkel point of view, natural numbers and integers are two extremely different beasts. So there, this obvious equivalence becomes something which has to be proved. And it will be ugly and long. So somehow we need to deal. So one needs formalization of mathematics, which can deal with this equality issue in a proper way. So let's consider now a more simple example. So there we had natural numbers and non-negative integers being the same. That's complicated. They're infinite sets. Let's look at something very, very primitive. So the first non-trivial case is the case of sets with two elements. Suppose I have one set with two elements and another set with two elements. They're clearly, in some sense, equivalent. So here is an example of a theorem about a set with two elements. So the theorem says that if I have a set with two elements, 0 and 1, then it has exactly 4 different subsets. And here is the proof that it has an empty subset which consists only of 0, only of 1, and the whole set. Now again, suppose I want to prove the same result about a set which consists of two elements called A and B. Obviously, I don't have to reprove it. It must be clear that this is the same as this. So that's a more simple version of the previous situation. Now, so there is one obvious way of dealing with it. Let's declare all sets with two elements to be equal to each other. Let's see what happens. It turns out that bad things happen. It's not allowed. And sorry, that's my ability to draw pictures on a computer has to be a little improved. But so let's look at these two pictures. So there is a circle downstairs, and then here are two circles above it. Here is a circle downstairs, and then there is one circle above it, but it's looped around itself. So I can look at these two things as drawings for two families of sets parameterized by the circle. So it's kind of maps from the circle to sets. Here I have a point x in S1. S1 is the notation for the circle, this lower thing. This is x. It goes to B of x, a set, this pre-image. And here happens the same. So if I move my point on the circle, the pre-image is always a set with two elements. Here, these two elements, then other pair of elements, and so on and so forth. The same is true here. Pre-image of every point is a set with two elements. So if all sets with two elements were declared to be equal, then these two families must be equal. If I have two functions which take the same values in the same points, they must be the same. However, they're obviously not, because in this case one actually has two circles up there, and in this case one has one circle up there. So it's just looped around. So the reason for that is that there are two different ways to identify the set with two elements with itself. So if I have one set with two elements and another one, I can either identify it like this or like that. Now, if I go back to my picture, if I start walking around the circle, when I move from x to the nearby point, they can kind of get canonically identified. So when I go the full circle, this set over here gets identified with itself in a certain way. So in the first picture, it gets identified with itself in the identity way. And in the second picture, it gets identified with itself by a permutation of two elements. So and somehow that's exactly what creates the difference between these two families. Some mathematicians in the audience may say that this example is a bit of a cheating. However, as it turns out to be, it's less of a cheating than it may look on the first side. So when we're talking about sets or some other composite objects, it leads to contradictions if we declare two similar such objects to be equal. So that's, of course, a classical thing in mathematics. And mathematicians have a name for it. It's called an isomorphism. So isomorphism is a particular way to identify two objects which can be identified in different ways. So one can write something like this by saying, to say that phi is a particular isomorphism between x and y. Now, so as it's written there, in the case of finite sets, two finite sets are isomorphic, meaning there exists an isomorphism between them, if and only if they have the same number of elements, which is what we would expect from some reasonable notion of equality. But there can be a bunch of different isomorphisms. So we have seen that there are two isomorphisms between two sets with two elements, but then the number grows, and there are like 120, I think, between two sets with 5 elements, and so on. Now, there is this very important principle, which is, we don't really, it is indeed like a keystone of mathematics. We don't really speak about it because we consider it to be an obvious thing, which doesn't deserve much speaking about. So I tried to write it in a somewhat formal way, just to be precise, maybe more formal than is good for this talk, but basically, if I have a theorem about x, and then there is some x prime which is isomorphic to x, then with the obvious replacement of x by x prime in the theorem should remain true. The standard formalizations of mathematics don't take this principle into account, especially the Zermelo-Frankel formalization. It treats all sets as being different beasts completely, and while of course one can define what does it mean for two sets to be isomorphic, a generic statement written in this formal language of Zermelo-Frankel theory about a set X might be true for X and completely false for another X prime which is isomorphic to X. So Zermelo-Frankel formalization, as well as basically all other formalizations, maybe in a lesser extent, does not respect this fundamental principle. And that's what makes it very hard to use in practice, like for some kind of proof verification, because again it means that if I prove a statement about X, and then my colleague needs to use it for some X prime, which he considers to be the same thing as X, because it's isomorphic, he basically has to reprove it. But now the story gets more sophisticated. So this isomorphism principle is an old principle. I think it was first formulated, it was called something like transfer of structure maybe, and explicitly formulated sometime in the 40s or in the 50s in one of the first Bourbaki volumes, when they tried to carefully write down all the known mathematics. Later on, it turned out that it's not exactly enough. I mean, a lot of people still think that it's enough, probably. But, I mean, a lot of mathematicians, but it really isn't. So when so-called category theory became, when category theory was developed, mathematicians encountered objects for which the notion of isomorphism didn't work very well. Same as equality is too rigid a notion for sets, for collections of elements. Isomorphism turns out to be too rigid a notion for some higher order collections. So there was introduced a generic word, equivalence. So one would speak about two categories being equivalent, meaning that they're indistinguishable. So that would be an analog of the isomorphism. And this thing actually goes up indefinitely, and there is this notion of an n-equivalence. We don't use it much in mathematics because it's not natural with respect to the existing foundations. And so we usually stop at the level of about 2. So I would say like 0 equivalence would be an isomorphism, 1 equivalence would be what we call equivalence, say, between categories, 2 equivalence would be equivalence, say, between two categories, but hardly anyone really uses it. So now let's kind of let me try to repeat what what one wants from good formalization. So one wants, formalization must respect these equivalences, not only equality, not only isomorphism, not only one equivalences, but all this hierarchy of equivalences should be respected by a good formalization. Otherwise, it's not what we need. Moreover, this somehow should be embedded into the formalization on the syntactic level. As I said, what was wrong with the Zermelo-Frankel? I said that it's a bad thing because I can formulate a statement about x, which will be true, but which will be false about x prime, despite the fact that x prime is isomorphic to x. And that's bad. So good formalization should have the property that it's impossible to formulate something in a way which is not invariant and with respect to these appropriate equivalences. And the cool thing that it seems that such a formalization can indeed be developed. And that's a big surprise, at least for me, and developed in a very cool way by bringing together ideas from very different parts of mathematics and even somewhat outside of mathematics. So there are several ingredients to this new approach to formalization. I'm starting with the one which is kind of the oldest. So one thing which was observed by Grothendieck, probably, I don't know the exact history of this stuff. Then it was eventually proved, by me in particular, many years ago. It turns out that this formalism of higher equivalences is equivalent to what's called homotopy theory. So the formalism of higher equivalences in mathematics is encoded in this theory of n groupoids, higher groupoids, infinity groupoids, whatever not. And remarkably, it's the same as this homotopy theory. Homotopy theory is a very mature, well-developed part of mathematics, which is in existence for at least 50 years, probably more, which deals with kind of discrete invariance of continuous shapes. I can speak about homotopy theory, but it would be a separate talk. Maybe I have one thing to say that, like, if here is a way to distinguish homotopy theory from other sort of sciences about shapes. If one has a shape of some sort, then this shape has two obvious kind of discrete invariants. One is its dimension. Like a line is one-dimensional, triangle is two-dimensional, so on. Another one is how many pieces it consists of. So the number of connected components. So if one tries to study the first of these invariants, sort of dimension and stuff related to it, one goes the geometric way. If one tries to study and generalize the second of these invariants, the number of pieces, one goes the homotopy theoretic way. So what happens is this equivalence between a theory of higher equivalences and homotopy theory, which combined with some other not very complicated ideas, shows that mathematics can be encoded in terms of homotopy theory such that this encoding respects the equivalences. So in the Zermelo-Frankel foundations, one encodes mathematics in terms of the Zermelo-Frankel objects, which destroys all equivalences. In maybe some topos-theoretic foundations. One encodes mathematics in terms of some analog of sets, which respects isomorphisms but destroys higher order equivalences. One can also encode mathematics in terms of homotopy theory, which now preserves all equivalences of all these different levels. Now, all and by itself, that wouldn't be very interesting, because homotopy theory itself is a complicated theory, and what good is it encoding one complicated theory in terms of another complicated theory? In order to use such an encoding for some kind of proof verification, we have to be able to develop a language, formal language, which would directly describe homotopy theory in the same way as Zermelo-Frankel theory directly describes the Zermelo-Frankel objects. The miracle is that it's possible, and moreover that it has almost been done before. Only the people who done it had no idea what they're doing. So if I go back for 1 second and look at this general diagram for formalization, so I want to place homotopy theory in the middle. Use here this encoding, which is basically, I guess, the simplest possible encoding which respects all the levels of equivalences. And that works fine. So what I need is the left-hand side. I need a language which would have a natural semantics landing in the homotopy theory. Right, so I should have not gone forward, but gone backwards from that slide. As was mentioned, there were two original computer systems for verification of mathematics. There was Mizar, which is based squarely on the Zermelo-Frankel theory. Actually, Mizar is a beautiful implementation of Zermelo-Frankel theory. The fact that it's not usable is, I think, a very good proof of the fact that Zermelo-Frankel theory is not usable. There was another one which was called Automath, which was done, or I don't know how it's pronounced properly, which was created by a person, I guess, from the computer science side of things, which was much more convenient. And in fact, it was created earlier, and the person who created it completely formalized and verified all the proofs in one of the standard textbooks on mathematical analysis using this system. So the language which he used was not the language in Zermelo-Frankel theory, not the first order logic, but something which, as far as I understand, he actually developed specifically for this purpose. I mean, this is now called, this was a language in the class of languages which is now called dependent type systems. I don't want to go very deep into this stuff, but the key thing is something like that suppose I have n-dimensional space. So I would write it Rn. That's a type. I mean, its members are n-dimensional vectors. But it's a type which depends on n, where n is a natural number. So it's a type which depends on a member of another type. So that's a typical example of what's called dependent type. Another more sophisticated example may be, say, the class of all algebraic varieties over a given field. That's a type which depends on the field. which is itself a member of the type of fields. Of course, in mathematics, in real-world mathematics, these dependencies and iterated dependencies are widespread. However, they were completely absent from the syntactic side of things until, as far as I understand, this work of De Bruyn on Othermass. Now, things were developing in sort of in an interesting way. Mathematicians never really took much. Mathematicians never really liked this Othermass formalization because he couldn't explain exactly what he's doing in the mathematical terms. But computer scientists love it. And there was a whole big industry which started from that thing and which is now growing very rapidly in the directions entirely unrelated to mathematics for most part. Not all the directions are, but for most part. It's mostly involved with, mostly related to the automated verification of software as opposed to proofs. And this is something very practical. There is a big group in Intel. There is a group which creates the software which NASA uses to avoid their more landers crashing somewhere. And it's a growing thing. It's also now people starting to use it to ensure the security of the systems and so on. The underlying theory is this dependent type systems, which was originated with the Othermass. The reason mathematicians, again, didn't like it very much was because no one could invent the semantics for this theory. So they had this box, but they couldn't connect it to anything whatsoever. And they knew that this box is very useful. But mathematicians don't like syntax without the semantics. And so, so it didn't go anywhere much in mathematical world. So it turns out that something like that might be possible. And that's the exact thing which I'm working on. So that's a tentative name for new foundations. It's called Homotopy. No, not foundations, new formalization scheme. Let's put it this way. It's called Homotopy lambda calculus. And the box, the syntactic side, is some language, some system which belongs to this class of dependent type systems with some quirks. The center of the picture is this world of homotopy types, which is essentially geometric. So I can draw pictures when I want to prove theorems here, or not even here, when I want to prove theorems about this language, about the logical theorems, I actually draw pictures. And then one can use this encoding, which respects equivalences, to translate general mathematical statements into statements about homotopy types, usually very special homotopy types. So my understanding is that this thing is really programmable, and that maybe someday in 5 or 10 years, when my next rotation for the faculty lecture comes, I'll be able to report and show some screenshots of how we now all do mathematics in this system. Thank you. Questions, please? I left plenty of time for questions. Yes?
So the interesting thing about this encoding into the homotopy type was that it was equivalence invariant in some sense. And so it seems like for this to be interesting, this new semantics needs to have some kind of equivalence invariance.
Yes, absolutely. Thank you very much. Yes, it's a kind of wonderful thing about this language. It satisfies this condition which was on one of the previous slides. It's absolutely impossible to even formulate a statement which is not invariant under our equivalences in this language. So,
can you give a simple example to demonstrate how it works?
which part of it?
The last piece, just that picture you had up there.
Hmm? Well, exactly how I write it depends on the exact nature of the. It's kind of more like a higher level language than lower level language. But well, ultimately, you write it just about the same way. I'm sorry that I didn't include examples. I wasn't sure I'll have time for that. You see that the real picture is that one has a low-level language, which is this, which can be very ugly when you really look at it directly. Then one may have a whole bunch of higher-level languages. One, say, for doing analysis, and another one for doing group theory, with proofs written in all these languages being automatically translated into this one and then verified by a proof checker which understands only this language. So if I wrote this sum blah 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 equals blah 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 directly in without any abbreviations in this homotopy lambda calculus, it would be pretty ugly. To make it usable in this sense, one needs an extra level of translation.
How much do you think the way papers are written today will have to be modified so that they could be processable when you do an automated refereeing system, the correctness part? How much will that affect the format the papers are written?
You mean the new papers which will be written? Not how to.
So that they can be processed by the system.
You know, when I'm writing about this, I'm writing a paper right now about this stuff. And beginning from about the middle of that paper, I do need to include some formal statements because I'm proving something about the language. It seems to be pretty easy, actually, to integrate it. So I just have a theorem which, if I have nice enough abbreviations, looks basically quite readable. Of course, a proof, if I want to include it, would look horrible. So the idea would be that the kind of low-level proofs will not be readable, but the statements will be readable. And the rest of the text is just like the usual text.
So I would imagine it would, the papers which one considers now as computer-assisted proofs, that they already somewhere match the kind of format, this stamp format, where there is a part that is really an automated verification.
Could you say it again, sorry?
I'm saying the papers like four-color problem of the Jacob Pulmar, which are partly computer-assisted, to some extent, you already match this format, that there is a piece which is verified by computer in an automated way, and nothing more than that, where there is no human intervention anymore.
I haven't really looked at these papers because, I mean, this four-color theorem and
This is what you were referring to when you mentioned the paper you were writing yourself, that there is some part which is checked by, which can be verified by a computer, or there is still a human intervention there.
so it looks like that. There is a text.
Right.
And then there is a definition, discussion, why I'm doing this, why I'm doing that. So the normal mathematical discourse. Let this be this, let that be that. Then at some point there is a theorem. The theorems in this language come into the form of, as it says, inhabitation of some type. So there is some expression which is understandable. You can read it, it fits into one line, okay? So it's easy to understand. And then there is a theorem, and I say, okay, this expression is inhabited. This type is inhabited. So I have to present this term which inhabits the type. This term may be 5 pages long of letters. So it's impossible to humanly understand. So there goes a reference to this file with this formal thing, and one can run it through a proof checker and verify that it is indeed a term of this type. But the statement as well is quite understandable. So that's the picture in my head.
The author of this paper, does he find the proof by conventional methods and then somehow translates it into that machine language?
So the workflow, so to speak, involves, I mean, we don't really know because it hasn't been tried too many times, but typically there's this interactive proof assistance, kind of editors of proofs, of formal proofs for this particular system. So a person, of course, at first one probably thinks of a proof in one's head, at least kind of the general outline of the proof, general layout, because I usually also think about my proofs on my couch in my office as opposed to sitting at a computer. So, so you first invent a proof, then you split it into smaller pieces. Then at some point, the place where it has to become, where it should become useful is when one has to go through technical lemmas. So instead of going through these technical lemmas on paper, one goes through these technical lemmas straight in this proof editor and writes them in the format which is directly verifiable by the computer. And I think that should be helpful also in terms of preparation, because one doesn't have to verify one's own proofs as many times as we now do, because if it has passed the check, it's done. One can move further. Yes?
Does this machinery give you the prospect of being able to have computers prove new theorems for you, things that you didn't know were true before?
It's not today. It depends on one extra ingredient, actually. It's not, depends on what you call new theorems, of course. Right? But it depends very much on one extra ingredient to this whole system, which is some kind of a database of existing knowledge, which is organized in such a way that it can be efficiently searched. And that's probably the most complicated part of the whole business. I mean, I think this is actually, despite looking weird, it's quite realistic, and we'll really see it happen soon. This database is a complex thing. So if one can build something like such database, then it's plausible that one can have a computer program which would sort of try to build it up. But it needs to know what to build up. Yes? No. Okay. From left to right, sorry. No, you go first.
In computer science, people consider the proofs that can be checked randomly. So, and somehow it seems that this gives you much more power. So you allow your checker to use randomization, and then you know that the proof is correct, but you have some tiny probability of making an error. And you say that you are not considering such.
I will answer. So the checker itself should be a very simple program. checker is not, the way these languages are constructed, the checker is a simple thing. It's kind of writing a proof checker for a given system is on the level of a senior thesis. So it's like a, I don't know, it's like something which verifies, it's like your tech, whatever, compilator. There is no reason to introduce any randomization in it. It works without randomization, and it just scans everything symbol by symbol, basically, and verifies that everything is composed correctly. So that's not...
You can show that in some cases, if you allow randomization, then this checking procedure can be much more efficient. So maybe it will be a kind of longer, so this is what is called probabilistically checkable proofs. And in some ways that you can really formulate precisely, every mathematical proof can be written in such a way that to check it, you just have to look at a few random places, and you will do some very simple computation. You will just check that several bits, there's some 8 to 0 or something like that.
Well, that might be an interesting direction of thinking, but I'm sure that for mathematicians to accept such a system, not only does it have to go and check every single bit, but there probably should be 20 different systems sitting in 20 different places in the world, which will have to verify 20 different times, one after another, for us to be sure that everything is correct. So I'm sure that, but there is another issue, which is not proof checking, but sort of this proof composition. Because when one actually writes a proof, even in the existing systems, one of course doesn't write it. This proof editing thing would be useless if one just had to write everything letter by letter. So this proof system, proof editing system always has some power of filling in the gaps. That basically also relates to the question of new theorems. So this is a question of how big a gap it can fill in. So all systems have ability to fill certain gaps. And it's extremely important from the practical point of view to make systems which can fill as wide a gap as possible. And that, because this is extremely time-consuming process, and that's where some kind of randomization, both in checking and in generation, will certainly be useful. I have no doubt about it. But not in the final checking. I just don't think the final checking is such a complex procedure.
Well, the proofs can be very long when you write them in a formal way. Looking at all of them may be difficult.
We'll see. That will need to play with an implementation. Yes.
We have lots of results, and some of them are incorrect, and they're already published, and it's not in the language that we propose. Is there any way of checking back those results before actually building up a new development of new theorems or something? We should be on the firm.
Well, it's an organizational. It's an organizational problem. I mean, you would, once a language is developed and becomes sort of goes through several generations of changes and adjustments and becomes indeed convenient, and people get used to it and it's familiar, then some people will have to go back and run the existing material, rewrite it in this language and run it through the computer.
So you mean it's going to be just rewriting everything that's done before and putting it through this checker?
Basically, yes. To some extent, I mean, yes. Yes?
When you use the homotopy theory, can you divide all segment to true and false, or something in between?
Why do I use homotopy theory? Can I mean,
Like problem with set theory, whether statements are always true or false.
well, here statements are also true or false to some extent. Although in set theories there are not well. This is a yet another side of things. There is this completeness and incompleteness. What is true? What is false? What is decidable? It's a completely different side of things. What I'm concentrating on is create a language which knows about these equivalences. That's the key thing for me. In the framework of set theory, it's impossible to do. Any other question?
So assume that you have a human proof of length and you translate it into this homotopy, lambda calculus language.
So I'm sorry, proof of what?
Assume that you have a human proof of length and a written proof.
Okay.
You want to translate it into this lambda calculus language. Will the length be something like c times n, or exponentially big n, or n squared, or
Oh, that's an interesting question. So we don't know about homotopy lambda calculus, but there is actually a lot of experimental material in the older formalization systems. And that's called something like de Bruijn coefficient. It's linear. It's linear, and moreover, apparently it's pretty invariant with respect to the hardness of mathematics, surprisingly enough. And the coefficient, I don't remember now the number. It depends on the language, of course. But for the original automass, it was maybe around 40 page by page. And I think for there is this Nurple system in Cornell, they claim to have a coefficient of about 6. Yes. Yes?
So what's the difference between a natural number and an integer?
No, wait. So in general, the difference is that natural numbers are only starting from 0, and integers also go in the negative direction. So that's the substantial difference. Now, on the other hand, if you want to define what is an integer, in mathematics, and even at school nowadays, as I know, one defines an integer as an equivalence class of pairs of natural numbers. So an integer is interpreted as a pair. Anyway, one writes a, b, and by that one means the integer a minus b. So when one formalizes it this way, integers don't look anymore like numbers. They look like something completely different. Even the non-negative integers, despite the fact that they're the same as naturals. And that's a problem. Yes?
Are you simply saying that mathematics is getting so complex that the human mind can't deal with it?
It's not the human mind, and it's not mathematics. It's more like mathematical. It's just getting, I don't know, too complex, too competitive. I don't know what. It's not like human mind cannot deal with it. It's that mathematical community cannot deal with it. It's not an individual problem. It's a community problem. Community cannot check the proofs produced by its members. It just doesn't have enough time, enough energy, enough will to do it. I mean, if we were paid for checking someone's proofs, this will all be in a trash bin, you know. Well, yes.
What you said, I think there's also a sort of interesting social question here. I mean, do we actually want proofs that no human can understand in finite time?
Yeah, it's. I would say the answer is yes. We would still want them. If we can get proofs of the same results which we can also understand, it would be better. But if we cannot, then yes, we do. That's my point of view. Thank you very much.